All right, welcome back to part 2. We're going to do a few more examples of factoring, like I said, so that we can get refreshed uh, on this topic, which we learned for most of us 2 years ago in Algebra 1, right? So now let's go ahead and try to factor some, special, these will kind of give us some special patterns once we notice the patterns, right? But for now, let's just do these kind of how we have been so far. So y squared minus 49. Now notice that there's no middle term. Normally you would have a y squared, which we do, a y, and that's what's missing here, and then a constant for the standard form. So we have our y squared term, and we have our constant term, we're just missing the y. So then let's rewrite it just so we're kind of doing it how we're used to. So I can say y squared plus 0y, because 0y is 0, which is nothing, minus 49. Okay, so now we can do what we have been so far. What are the factors of 49 that add up to 0? Well, the factors of 49, we have 1, and in this case, negative, so keep that in mind. 1, 7, and 49. Those are the only factors. Well, we know that, the pairs, when I do these in pairs, I have 1 and 49, and then 7 times itself, because 7 squared is 49. We know that this one is, the constant term is negative. And remember in the example we just did, part B, whenever our constant is negative, that means that one of these has to be negative because, again, the only time we can get a negative from multiplying two numbers is by one of them being positive and one of them being negative, all right? Well, when we do that, when we make one of them negative, usually we look at this one to see, oh, is the bigger one going to be positive or is the bigger one going to be negative? We can't really tell because there isn't no middle term. And here it's ambiguous because I can put a plus 0 or a minus 0 and it would be the same thing, right? Well, when we subtract the two factors, we have to get 0. What's the only way to do that here with these two pairs? Well, no matter how you do it for the first one, there's no way I can get 0, right? It's either going to be 48 or negative 48. So then it has to be this second pair. Negative 7 plus 7, negative 7 plus itself, is 0. So that's the only way I can get this middle term to be 0. So then when I factor it, I get y minus 7, y plus 7. All right, and there's my answer. Okay, so now, kind of hold on to that because we'll talk about it in a little bit, but let's just do a few more examples. What about this one? We can do it the same way we have been doing the other ones. Factors of 9, 1, 3, 9. So our pairs are 1 and 9, 3 and 3. It's a positive 9, so they're either both negative or both positive. But when we add them, we get a positive 6. So they're both just going to stay positive, right? Well, when we add those, we get 10 and 6. We want them to add to be 6. So it looks like this is the correct pair. So when I factor, I get b plus 3 times b plus 3. Okay, now sometimes you might see this as b plus 3 squared. And we saw that a little bit in 4.2 when we worked with the vertex form. We had that binomial squared. Either one of these is correct, right? You can write whichever one makes you happier, right? But just know that both of these are the factored form of b squared plus 6b plus 9. All right, 2 more examples. So then, oops, spoiler alert. I'm gonna put it back down. So then let's look at this part E. R squared plus 81. All right, so we need, remember we can rewrite this if we wanted to as R squared plus 0R plus 81. We need factors of 81 that add up to 0. So we know it's 1 and 81 is one of the pairs. And then 81 is 9 times 9. Those are our only 2 factor pairs. Now, 81 is positive, so they have to have the same sign. They're either both negative or both positive. And since it's technically 0r, we don't know whether it's both negative or both positive. So we got to just try them all. Well, 1 plus 81 is 82. And 9 plus 9 is 18. And if I stuck negatives in front of each one, and I did -9 plus -9 and -1 plus -81, well, that only changes the sign of the result. It doesn't ever give us 0. So then this is another one that cannot be factored, or as we called it, prime. Okay, so we can't factor this one, even though it looks a lot like part C, right? Just notice the difference. In part C, I was subtracting, but in part E, I was adding. Okay, so we'll want to hold on to that for a few minutes. But let's look at F before we talk about that a little bit more. So F, m squared minus 10m plus 25. Same idea. Factors of 25, so that's 1 and 25, and 5 and 5, that add up to -10. Again, since this is a positive number, they're either both going to be positive or both negative, but since this is negative, that means they're both negative. Okay, so when we add these pairs together, which one gives us -10? Well, this one, of course, -5 plus -5. So that means that our factors are m minus 5 and m minus 5. Kind of like this one with the b squared plus 6b plus 9, I can rewrite this if I wanted to as m minus 5 squared. All right, either one works. Okay, so now hopefully you kind of see a pattern here, right? We've been working a lot with, if you look at the constants in each of these examples, they were all perfect squares. Okay, we have, what does this look like? I've never used this pen before. Oh, that one looks weird. It's got a little galaxy design to it, sorry. Perfect squares, we have 25 is a perfect square, 9 is a perfect square, 49 is a perfect square, and 81 is a perfect square. All right, they're all perfect squares. And those are kind of, we can use those to our advantage because if you notice, they all kind of had a pattern. Whenever I had y squared minus 49, that was just 7 and 7 with opposite signs. Whenever I had not a perfect square 9 here, those were, b plus 3, b plus 3. Now, but it's crucial, like I can't just have 9 here and say, oh, it's automatically b plus 3 and b plus 3. 3 plus 3 is 6. So this has to be a 6 in order for me to do that. Well, 3 plus 3 is the same thing as 2 times 3. Same idea here. 5 plus 5 is 10. 2 times 5 is 10. And now notice that in our part E, we couldn't do it because this was a plus. It has to be a minus. Now, maybe you remember these again from Algebra 1, but it's these kind of special factoring patterns, okay? When we have a difference of squares, we usually have something that looks like a squared minus b squared. Now notice that a and b are just placeholders, right? They can be anything. They can be, they can both be variables. One of them can be a variable, but they really can be anything. But so far what we've seen is, we saw x squared minus 49 up there. Another example would be like x squared minus 9. As long as this first term is squared and the second term is a constant that is a perfect square. And again, remember, it doesn't have to be a constant, but that's kind of how we've been seeing it so far. Another one, t squared minus 1, that's also an example of difference of squares. And the way we can use that to our advantage is that it always factors to a plus b, a minus b, right? And we saw that up here with the x plus 7, x minus 7. With x squared minus 9, well, what do I square to get 9? I square 3. So that would just be x plus 3, x minus 3. What do I square to get 1? 1. So this is t plus 1 and t minus 1, right? So that's kind of how that pattern plays out. And we have the same thing with our perfect square trinomials. Now notice the pattern. It's a square term in the front, a square term at the end, and then it's 2 times this this 5. 10 was 2 times 5. Up there, 6 was 2 times 3. So it's 2 times the, the factor we ended up here. And actually, it's also technically 2 times the first one, because it's actually 2 times the m and the 5 because we have the m included there. So before I keep jumbling my words, let me write it out for you. So we have, a squared. In this case, let's do the positive one first, plus 2ab plus b squared. That is our perfect square trinomial. That's our a plus b, or a plus b squared. All right, so in this case, our a is m, and our b, well, sorry, and the one above this, our a was, let me scroll up here. Our a is our b. It's gonna be a little confusing because I use b here. Our a was b, our b was 3. So then a squared is b squared. 2ab is 2 times b times 3. 2 times 3 is 6 times, the b. And then our b was 3, so b squared is 9. And then we can use the same thing when our middle term is negative. We just have to adjust it a little bit. A squared minus 2ab plus b squared is equal to a minus b, a minus b, a minus b squared. Okay, and it's a little bit easier to see with f because, sorry, I meant to pull up, not draw. It's easier to see with f because we're not dealing with the b as the variable here. Our a was m, and our b was 5. So m minus 5, m minus 5. A squared, that's m squared. 2ab, that's 2 times a, which is m, times 5, which is b. 2 times 5 is 10, times m is 10m. And then b squared is 5 squared, which is 25. All right, so that's the special patterns. Now, if you're kind of looking at these patterns like this is kind of, it's making me go cross-eyed. There's too many letters to keep track of. You don't have to use these. Now, these can be a little bit of a shortcut for those of us that are a little lazy and we kind of understand how the patterns work. But if you don't understand how these patterns work, then you can still do it how we have been doing. Find the 2 factors that add up to the middle term. Sorry, find the 2 factors of the last term, the constant, that add up to the middle term, the power to the 1, the m, the x, the t, etc. Right? So you can use this if you want. You don't have to. It's just something we want to notice as we continue factoring. Okay? Go ahead and meet me in the next video where we use the factoring to actually solve these quadratic equations. Okay?